everybody, and welcome back to Unit 6, Lesson 4, which is about properties of integrals. So up until now, we've been using the idea of integrals being an area and geometry formulas, like the formula for the area of a rectangle or a trapezoid or a triangle or a semicircle, to find the values for integrals. This video is going to be the first video in several lessons where we're going to start to use algebraic methods to find the value of an integral. Now, we're going to start today with what are called properties of integrals. Properties of integrals go back to the fact that integrals are areas on a graph, and they use what we know about areas in order to take known values and find the value of a new integral. So, for example, before I go over the properties, on the second page of your notes, you can see kind of how these problems get set up. We are going to be told certain values that we already know. For example, we might already know that the integral from -1 to 1 of the function f of x has an area of 5. We're going to try to use those known values to find the values for integrals that are related but different from the ones that we know. So, for example, you'll notice that this integral looks a lot like this one with some slight changes, right? The bounds are reversed. But we can use the fact that we know this area to find this area. And that's what these properties are going to help us do. So for each of these properties, I'm going to go ahead and sketch the properties or kind of explain the properties and then sketch a picture for why that makes sense. The first property is what's called order of integration. Order of integration says that if you take the bounds of an integral and you change the order of the bounds. So the original problem here says the integral from a to b is worth s. The new integral says the integral from b to a. You can see the bounds flipped. If you do that, then the area changes signs. So instead of s, it would be -s. Now, the reason behind that is this. If you think about an integral, this first integral says start from a and go to b, and we know that that area is worth s. And you're going from left to right. If you take that same integral and you switch it so that instead of going from left to right, you're changing the order, so you're going from right to left, that is why the area becomes negative, because you're going backwards. You're going from right to left instead of left to right. Another way that you'll sometimes see this come up is that we know the bottom number here should always be the lower number. If it's not, if the lower number is on the top, then what that means is it makes your area negative because you're going backwards. This means that there are now two ways to get a negative area. You could have an area that's below the x-axis, but you could also have an area where your x values are reversing the order. You're going backwards, and that means you get a negative area from that as well. So that negative is really telling you about a direction. So you're going from right to left, you're going backwards, or it's just the opposite of an area that you already know. Now, the zero property says that if you have a function and you start your area at A and you also end your area at A, then that means that the area is worth 0. And this should make sense because if you think about starting and also ending at A, if you start from A and you end at A, then your portion of your graph that you're looking at is just a straight line, which doesn't have an area. It doesn't have like a size to it because it's just a vertical line. So there's no width for your subsection. I should make a note here that this is because you're going backwards. That's what makes this have a negative answer. Okay, now a constant multiple means that you're taking your original function and you're multiplying by a number. If you know that the area of your original function is worth s, then the area of your new function would be worth k times s. So basically, if you multiply your function by a number, you're changing the height so that it's that many times bigger. That's going to make your area that many times bigger. Next, we have our sum and difference rules. Now, sum and difference means that if you have two functions being added together inside of an integral, that you can just add their areas together. So if I know the integral from a to b of f of x, and I know the integral from a to b of g of x, then when I add those functions together, I can just add their areas. So integral from a to b of f of x dx, and then either add or subtract, depending on what it says in the original problem, the integral from a to b of g of x dx. So you can just add different functions and then add their areas to get the answer. The addition rule is talking about the bounds. So what I want you to notice here is that the bound that's the top of this integral is the bottom of this integral. Now, if you imagine this on a graph, what you're basically doing is looking at a graph where you know the area starting from A and ending at B. That's a known value. So you know this area. And then you also know the area starting from B and ending at C. If you want to get the area of the whole thing from A all the way to C, you can just add those two areas together. So when the top number here matches the bottom number here, we can say that now we know the total area from A to C, all the way from A all the way to C, because we can just add those two areas for that function together since they connect in the middle. Like you're just now extending the bounds of your integral. Last but not least, when you're adding a constant. So let's talk about what adding a constant does to a graph. Let's say your original function, f of x, looked like this. From A to B. When you add a constant k, what you're doing is taking that original function and you're shifting it up that many spaces. So when you add a function k, what you're doing is you're taking the original function you already had and you're just moving it up. That creates a new rectangle of area below your function because you shifted that whole region of the graph up. So in order to find that new area, you're going to take the area that you already had from A to B of f of x, and you're going to add the area of the new rectangle. Now to find that area, you're going to do base times height, which is going to be k for the height times, to find the size of that base, you would do b minus a. Like if that was from 1 to 4, you would just do 3 because it'd be 1 minus 4 or 4 minus 1. So when you add a constant, you can't just add that number to the original area. You need to add in a rectangle whose height is that number to the original area. So let's look at some of these problems and see if we can figure them out using these properties. So the first problem here says that we know that the integral from -1 to 1 of f of x is worth 5. We know that the integral from 1 to 4 of f of x is worth -2. And we know that the integral from -1 to 1 of h of x is worth 7. So let's see if we can use those properties to figure out some integrals that we don't know. So for problem number 1, it says, can you find the area between 4 and 1 for f of x? Now you'll notice that the area from 4 to 1 is this integral is very similar to this integral. There's the integral from 4 to 1, and this one is the integral from 1 to 4. In other words, this is just this area, but going backwards. That means that in order to find that area, because we're going backwards, we're just going to take the original area we already knew and we're going to make it negative. So it would be negative the area we already had, which was -2. In this case, that means that the answer would now be +2. So you're changing the sign because you went in the opposite direction. For problem number 2, you'll notice it says, let's try to go from -1 to 4 of f of x. Now, this first f of x integral goes from -1 to 1, and the second one goes from 1 to 4. In order to go from -1 to 4, I need to combine those. One of the best ways to do this problem is to visualize it on a number line. So if we know that going from -1 to 1 gives us an area of 5, and we also know that going from 1 to 4 gives us an area of -2, then to get the area from -1 to 4, we can just add those two answers together. So we would do 5 plus -2, which would give me 3 as my final answer. Next, for problem number 3, it says find the integral from -1 to 1 of 2 f of x plus 3 h of x. Now, I know the integral from -1 to 1 of regular f of x, not 2 f of x, is 5, and the integral from -1 to 1 of h of x is 7. Because my properties say that when you multiply your function by a number, or when you add two different functions together, you can just basically use arithmetic. You can multiply the answer and add the answers. We're going to go ahead and do this problem that way. So the first thing we're going to do is 2 times the answer we already had for f of x, which is 5, plus then we're going to do 3 times the answer we already had for h of x, which is 7. And that means that we get 10 plus 21, which is 31. Now, the last problem here, we're adding a number, not a different function. It's not f of x plus h of x. It's just a number to my f of x function. So what that does is it shifts your graph up. So the first thing I'm going to do is figure out the area from 1 to 4 of just f of x, which I already know is just -2. It says that in the original problem up here. Now, I also know that adding that 7 is going to create a rectangle of area where I shifted my graph up 7 spaces. And I'm integrating from 1 to 4. So the rectangle that I'm creating is this sized. It goes from 1 to 4, and the height is 7. To find the area of that rectangle, I would just do base times height. So the base would be 3, the height would be 7, which means I get -2 plus 21, which is 19. All right, last but not least, let's try one more problem where we have a little bit more complicated of information. So we know that the integral from 0 to 2 of f of x is 4. We know that the integral from 0 to 1 of f of x is 1. We know that the integral from 1 to 2 of g of x is -1, and 0 to 1 of g of x is 3. So we know stuff about f of x, we know stuff about g of x. Now we've got to figure out some new information using what we already know. Problem number 1 says the integral from 0 to 1 of 2 f of x plus g of x. Well, I know, I'm going to make these colored so that it's easier to see which ones I'm referring to. Pink, orange, green, and purple. Or actually, I'm going to use blue, and then I'll use purple for my work. Okay. All right, I know based on the orange function here that the integral from 0 to 1 of f of x is just 1. So same bounds, only now I'm multiplying by 2. And I know from the blue function here that the integral from 0 to 1 of g of x is 3. So same bounds. So I can use that to find my new answers. So I'm just going to do 2, which is the number right here, times the original f of x area, plus my g of x area, which is just 3. So that's going to give me as my final answer the number 5. Okay, next we say, let's find the area from 0 to 2 of g of x. Now, I know some stuff about g of x. 1 to 2 is worth -1, the area from 0 to 1 is worth 3, but I don't know about the area from 0 to 2. So what I'm going to do is sketch on a number line what I do know, because that's going to help me visualize whether I should add or subtract or whatever the numbers I already have. So I know on my number line from 1 to 2, from 1 to 2 is worth -1. And I also know that from 0 to 1 is worth 3. I want to know, how can I go from 0 to 2? Well, if I've got the little piece and the little piece, I'm going to add them up to get the big piece. So I'm going to do 3 plus -1, which is going to give me 2 as my area. For number 7, I'm integrating from 1 to 2 of -5 f of x. Now, I don't know the integral from 1 to 2 of f of x. I have 0 to 2 and I have 0 to 1, but I don't have 1 to 2. I know that my property says that if I did know that number, I would just do -5 times that number. So my next step is going to be to figure out the integral from 1 to 2. Just like I did for number 6, I'm going to sketch a little number line here to visualize these areas. So I know that for f of x, if I go from 0 to 2, that area is worth 4. And I also know for f of x that if I go from 0 to 1, which is in between 0 and 2, that this area is worth 1. Well, if you know those two things and you want to figure out the area from 1 to 2, then you're going to need to do the big distance, like the big area, minus the small one. So 4 minus 1 is going to give me that area is 3. That means that my answer here would just be -15. Last but not least, the integral from 0 to 1 of g of x plus 5. Now I know the integral from 0 to 1 of g of x is just worth 3. But when I add that 5, I'm adding a rectangle of area. So if I were to visualize this, that 5 is how many spaces I'm shifting up my function. So I'm now up here at 5, and I'm integrating from 0 to 1, which means I've got this rectangle that I'm shifting up. I've added that area. The base of that rectangle is 1 and the height is 5, so the area total would be 8. Now, there are some things you're not allowed to do. So one of the big things that often comes up is you're not allowed to just multiply. If you knew the integral from 0 to 2 of f of x, and you knew the integral from 0 to 2 of g of x, you would not be able to just multiply those answers when you multiply the functions, because multiplying the functions changes which function you're working with. It actually makes, like, if it was x squared and x cubed, it makes it an x to the 5th. It's a totally new function. So you are not allowed to just multiply the f of x answer times the g of x answer. That is not allowed. So watch out for that. Oftentimes, we'll give you a question that says true or false. Is this equal to this? And you're going to have to say, no, it's not. All right, that is it for today. Thank you guys so much for watching, and I will see you soon for some practice.